In this lesson, I want to introduce you to James Clerk Maxwell and a set of equations known as Maxwell's equations. So James Clerk Maxwell was a Scotsman, and as you can see from the date shown, he unfortunately passed at the relatively young age of 48 due to complications from abdominal cancer. But on the brighter side, he lives on forever as a major figure in the study of electricity and magnetism, and in fact sort of unified the study of electricity and magnetism in just one set of 4 equations. So let me write down the first of Maxwell's equations and see if you recognize it. One of Maxwell's equations says the complete surface integral found by taking the dot product of electric field and area vector is equal to 1 over epsilon naught, that quantity known as the permittivity of free space, multiplied by the amount of charge that lies inside of the closed surface area. But of course you recognize this as Gauss's law. So wait a minute, is it Gauss's law or is it Maxwell's equation? Well, hold on. Let me give you another equation. The integral of, not any integral, once again, a complete closed surface integral found by taking the dot product of magnetic field with surface area is equal to 0. This is a way of saying there are no magnetic monopoles. Now, for comparison's sake, let's talk about electric monopoles. Well, I believe a proton is an electric monopole, right? It's just one type of charge. It's not a dipole. It's not a positive and a negative. It's just a single positive charge, and protons definitely exist. And if we were to choose some imagined surface, now this has to be a 3-dimensional surface, because that's what we mean with this symbol on the integral sign, is a completely closed surface area. So I don't know, I guess I can draw that little symbol to say that's 3-dimensional. And so there is a net amount of, isn't the name for this flux, right? There is a net amount of flux that points outward. Now let's talk about magnetic monopoles, whether or not they exist. I know there's such thing as magnetic poles. A bar magnet, for example, is a dipole. It has a north and a south. So if I were to draw a surface that encloses that bar magnet, here we go, then how much magnetic flux do I have? Well, let's see. There's some outward flux, and there's some more outward flux, and there's some more, oh, it looks like I've got flux. But then again, that field line's going to wrap around on itself, and that outward flux over on this side of my surface is going to be canceled by the inward flux over on this side. And the fact that magnetic field lines always form complete loops suggests that whatever amount of flux comes out, which maybe we'll say positive, is always going to be canceled by the inward amount of flux that we'll call negative. And so indeed, as long as your surface is totally closed, then there's always going to be a 0 net amount of flux. But I'd like to challenge that idea. Let's see. Wait a minute. Why did I pick such a large Gaussian surface? What if I had my bar magnet, and instead of drawing a surface that surrounds the whole thing, what if I just draw a sphere that only goes this far, so I only enclose the North Pole and not the South Pole? Then that should be a monopole, right? Field lines will go out, so we've got some positive flux. Oh, but wait a minute. The field lines wrap around and they come back in. Yeah, but they come into the south and they don't come back into my Gaussian surface. So it looks like I have a net flux, but wait a minute. I think you caught me on this one. That field line doesn't stop at the South Pole. As we've said before, field lines continue to go through the internal magnet, and there they go. They enter my Gaussian surface on this side, so there's no escaping it. There's no way around it. The amount of outward flux will be canceled by some amount of inward flux. And in fact, you realize this. You couldn't take a bar magnet and just get a hacksaw and cut it in half and say, aha, now I have just south pole over here, and over here in my right hand I have just north pole, so I have two monopoles. But you know, the reason for these magnets really comes down to, well, the source of all magnetism is charge and motion. And actually, stay tuned for one of my later video lessons, or you can fast forward to it after you watch this one. We'll explain why the bar magnet is a magnet, where the moving charges are. You might be able to guess that the moving charges are actually the electrons that are in orbit in every single atom that we're picturing here in the material. And so if the atom has a nucleus like this and the electron orbits in that plane, then it has a magnetic dipole moment, vector mu, and so that's the north end and that's the south end, and then this atom also has electrons orbiting in that plane, and so there's the north and there's the south. In other words, every atom itself is a dipole with both a north and a south. So when I make this cut right here, this is still a north pole and this is still a south pole. So you don't have to take my word for it, but I do believe nobody has ever found a magnetic monopole, and this equation is just a way of stating that mathematically. I'm going to write those two equations again. I'm going to put these all together in one list. So the first two equations that form Maxwell's equations, one you just recognize as Gauss's law. The integral of E dot dA is 1 over epsilon naught times the amount of charge enclosed. So here's a new one. There are no magnetic monopoles, so the integral of B dot dA is equal to 0. What about B dot ds? What if I try to take the integral of magnetic field and distance as opposed to magnetic field and area? But again, notice I put a complete loop on my integral sign. So here, better I illustrate this. So what if we say current is flowing in a long straight wire? Now in our last video we derived the equation for this, and in a previous video we saw that the magnetic field lines form circular paths around the wire. Anyhow, if we say, when using this first equation known as Gauss's law, if we picture the electric field lines as a bunch of lines pointing outward, then we have to imagine some totally closed surface, and we call that a Gaussian surface. Here, I'm not going to make a surface, I'm going to make a loop. I say loop because it has to go all the way around. So here's my loop. I'll make a loop that's just a path that goes all the way around. So there's no area to speak of. Well, I guess there's a cross-sectional area, but ignore that. What we're talking about is if I just take a little portion around that ring, that's ds. And then another little portion around, there's another ds, and another ds, and another. And so if I were to integrate all the way around ds, I guess I would get something like 2 pi r if that imagined path has a radius of r. So I'm going to refer to that not as a Gaussian surface, but as an Amperian loop. All right? Well, here's the thing. We already know that the magnetic field lines around a wire, use the right-hand rule, point your thumb in this direction, and then your fingers go in circular paths. So I guess it goes that way, right? Yeah. And these field lines continue. The farther afield you get, the weaker. So anyway, there are some magnetic field lines that lie along my Amperian loop. So there's a dot product between magnetic field and the path that I've chosen. And that value depends almost entirely on what the value of current is that flows in the wire. In fact, that's really all it depends on. Here's the way we state this equation. The total product of magnetic field and path length, as long as it's along any closed loop, is equal to, now check this out, I think you'll like it, the result becomes very similar to Gauss's law. Instead of 1 over epsilon naught, it's mu naught. And instead of the amount of charge that lies inside a Gaussian surface, it's the amount of current that's enclosed by the Amperian loop. This is called Amperes Law, and it has some similarities with Gauss's law. Okay, let me number these equations. 1, 2, 3. And like I said, Maxwell's equations is a set of 4 equations. So I wonder if you can guess what the 4th equation looks like, at least on the left side of the equation. Any ideas? We have an integral of electric field with area, an integral of magnetic field with area, an integral of magnetic field with path length. So what remains? Right, the integral, and once again, a closed loop integral, product of electric field and path length. Well, turns out that's a special equation in the study of electromagnetism as well, and this is equal to negative n ddt, the integral of b dot dA. And there's a name for this equation. It's called Faraday's Law. The full name of it is Faraday's Law of Electromagnetic Induction. And that's actually the, we spend a full unit of study, right? Here we are in the middle of Unit 4.2 on magnetism. In Unit 4.3, we're going to study this 4th expression, Faraday's Law of Electromagnetic Induction. Now, wait, you might have caught something here. You might say, wait a minute, there's an integral of BdA, and I thought you just said a moment ago that the integral of BdA is equal to 0. A closed loop integral of BdA is equal to 0, because like we said, if you try to enclose any magnet, magnets are always at least dipole, and so there's always as much outward field as there is inward if the area is totally enclosed. But you could have something like this. You could have a bar magnet, and then maybe like just a loop of wire. Actually, let me draw that again. How about nearly a full loop of wire, and then connected here. And then maybe you connect this across some resistor, some device you want to power. Now, I think this resistor isn't going to get any power at all because I don't see any battery anywhere in the circuit, right? However, there are field lines that pass through the surface area of this coil. There's a magnetic field line that passes through the area and passes through and passes through, and then these wrap around on themselves, but because it's an open area, not an enclosed area, there's a net amount of flux there. Well, here's the idea. If this magnet were to start to vibrate back and forth along this axis, then the amount of that product of magnetic field and area would decrease as the magnet pulls this way, and then as the magnet is brought back in this direction, that product of magnetic field and area would increase again, and as long as you pull this magnet back and forth, you'd constantly be changing this value, and so there would be a rate of change to the product of B and dA. And it turns out then that would be equal to the integral of E dot ds. And you might recognize E dot ds. Didn't we say way back when in our study of electrostatics that a potential difference of voltage is equal to the integral of E dot ds? We might have said negative the integral of E dot ds. So there's something to this. Whenever there's a rate of change of what we call magnetic flux, it tends to generate a voltage. So you don't need a battery to make current flow in a loop of wire as long as you have a magnet that can move back and forth. So that's a sneak peek at Faraday's Law. In any case, I think we need to write all these equations one last time so you can see them in one view. Maxwell's equations, 1, 2, 3, 4. One of them has to do with the integral of E dot dA. Another one is the integral of B dot dA. Next one is the integral of B dot ds, and the last one is the integral of E dot ds. So the first one we already know from earlier this semester. This is 1 over epsilon naught times q, and that's Gauss's law. So here's something new. Gauss's law for magnetism is a way of implying there are no magnetic monopoles. So the third one is key to this unit of study on sources of magnetism. It's called Amperes Law, and it suggests that the integral of B dot ds is mu naught times the amount of current enclosed by an Amperian surface. And the last one says that voltage comes from a rate of change of magnetic flux. The first one is Gauss's law for electricity. The second one is also Gauss's law, but Gauss's law for magnetism. And this last one is known as Faraday's law. So when we put them all together, we form a set of equations that gives us a comprehensive view of our study of electricity and magnetism, known as Maxwell's equations. In our next video, you're going to see how we can apply Ampere's law to make some problems much easier to solve.